Okay, welcome everyone to this continuation of Lie theory. Lie theory. Very fancy subtitle here. One parameter subgroups and flows. One parameter subgroups and flows. But essentially the whole video will just be about the best friend, everyone's best friend. I hope it's everyone's best friend. The exponential map. Exponential map. Can we find an image of the exponential map? The exponential map. So this guy here, we'll see that later. So the exponential map is like the most important map for Lie groups in a certain sense, of course. What most important is very weak, and it's based on the exponential. This guy. Oh yeah, this guy. This guy looks good. Well, this guy is not maybe not the exponential I'm looking for. I'm more looking for this exponential here. So also everything sounds very fancy. Hopefully it will not be all that fancy. Very nice exponential. Exponential growth is also something fun. So let's have a look at exponential growth. Oh, beautiful. Look at that, exponential growth. Beautiful. Do we have an example of exponential growth? Yeah, this one. So exponential function is everywhere, of course. But anyway, so let's have a look at what we are going to do today. Remember that we want to describe matrix groups essentially. So if you just keep matrix groups in mind and really just general linear group, so just invertible matrices, then you will be fine. Everything will be invertible matrices anyway. So these one parameter subgroups. So one parameter essentially says you have a time that you can vary. No? One parameter subgroups. Actually, the goal you want to keep in mind is that we want to describe somehow curves in our little G. G is our Lie group, right? And one parameter subgroups are the ones that are somehow compatible with multiplication. So essentially, it should be something like s plus t for my map here, and the map usually goes from something like depends a bit how you want to do it. But let's say it's something like my little map here, the one parameter map goes from. Oops, that's not what I wanted to do. No, I want to draw. It goes from something I want to draw. Excellent. It goes from something like, let's say, R to our little group, or some people like C to our little group. Essentially, I think of this as like, here's our little group, here's our little group, and then we have some map, whatever. Let's say we start at the identity or some condition here, somewhere is the identity. We start here, and then we have a one parameter thing, so we go somewhere, and maybe we come back, something like that. So literally, just a flow in your group. So and hopefully this picture is reasonably clear. This is my absolutely silly drawing of a Lie group, just a blob, and a pass in that Lie group is essentially a one parameter subgroup. That's not quite what we want, well, because pass can be pretty crazy. So you have literally a pass that respects the group law. That's essentially what it is, right? A motion in my little group that is consistent with our group law. And these are plenty of examples what you could see, whatever it could be. So one of them, right? So one of them could be some pass like this, and it has some properties related to the group, and the group is collecting some symmetries. So it's not something completely random. Yep. And kind of the interesting thing that we will do is we just look at the infinitesimal data, which is like the velocity, essentially the derivative, right? The velocity. And we will call the collection of these the Lie algebra. Kind of an interesting thing to do. We essentially look at kind of all the flows and how fast they are at the identity, the velocities, and then you just collect them into a thing, okay? And that thing will actually have some additional structure that reflects almost one-to-one your group itself, which is kind of a crazy thing. Okay, hopefully that was clear. We're looking for these guys, and up to conventions, you can just think of this. I'm usually, as I said, always into the complex numbers. Very questionable life choice, by the way. But anyway, for pictures, this is somehow much nicer. And I just think of it as like a one parameter. So the time here, let's say t, you send t to something, and the t here is a time parameter, and you just walk here through, let's say in time, through somewhere. And keep in mind that because you respect the group law, it actually has some reasonable structure. It's not just a random thing. And usually also we want this to be smooth, yeah. So because, well, G is smooth, yeah. So nothing too crazy, but somehow something that reflects, that reflects our Lie group itself. And where does it come from? Essentially, it comes from the idea of solving ODEs. So ODE. So what is an ODE? In case you don't know, an ordinary differential equations. ODE mass, and then something like a differential equation, an ordinary differential equation. No? And the standard one, we'll see that in a second, is everyone's favorite. Anyway, so somehow you want to solve something not too difficult, like the motion of this little dot here if you just throw a ball or something. And the standard one, here it is x prime is equal to x, or a scalar times x. Problem with this is, there's not really a problem with it. Everyone likes it. Its solution, by the way, is the exponential function, essentially. And yeah, well, that's almost what we need to do, because what we really have is something matrix values, because we think about matrix groups. So maybe we want to do something like x prime of t is a times x of t, where a is a matrix and everything here already happens in matrices. And this is like a linear system of motions in the general linear group. Yeah. And of course, if you just find the essentially unique solution to that problem, you will find that it respects our little group law. Yeah. So essentially what you can think of is we want to study continuous symmetries. So essentially we want to look at solutions to differential equations instead of polynomial equations like Galois theory. Differential equations, and solving differential equations essentially gives us those one parameter subgroups of our little Lie algebra. This is where this idea comes from. So these one parameter subgroups are essentially the collection of solutions to differential equations, if you want, in a certain sense. Hopefully that makes some. Hopefully that's reasonably explicit. And of course, the one solution that comes to mind here. Let's look at this equation. The one solution that comes to mind for x prime equals a times x, and a is just a scalar. There's one solution that hopefully comes to mind. It's the exponential map, right? That's hopefully true. And yeah, essentially it's this picture. So this looks like an exponential. And yeah, so the ratio here and the ratio at this point are the same. So kind of the speed at one point is there's literally that equation here. So literally this differential equation. So it's our friend, everyone's friend. So if it's not your friend, I'm very sorry. It's usually everyone's friend. So it's very amenable to everything. It's everyone's friend, the exponential function. In contrast, we will see that one as well. Hopefully not today. Hopefully not today. Its opposite, the logarithm. Very useful thing. Oh god, very useful, but so bad. Oh yeah. Nobody's friend. Oh, the logarithm. Nobody likes the logarithm. If you like the logarithm, then please turn off the video. Anyway, just kidding. So the exponential function, and you can just literally do it by using its standard Taylor expansion. Just now you have a matrix instead of a number. Yeah? And it's like the universal way to integrate a constant generator. So why not define the E of A to be that thing? And A, you can think of A as somehow an element in the Lie algebra right now. And an exponential is now an element in the Lie group. We'll see that later, right? So the key map is here. T goes to T to the A. So T goes to T to the A, and T to the, this E to TA is actually an element in our Lie group. And we kind of found a one parameter subgroup in GLN here. I'll show you a nice example on the next slide. And of course, because it's an exponential thing, it satisfies our favorite equation. So in particular, it satisfies this type of thing. It turns addition into multiplication. In case you wonder, that was the exponential function that turns addition into multiplication. Which was the original reason why the logarithm was so interesting, because it does the opposite. It turns multiplication into addition. But I just BS'd on the logarithm, so I won't pull up the logarithm again anytime soon. Probably that's a lie. So let's have a look at some examples. Literally symmetries. So if you take this matrix, for example, which is rotation. Oh, we can do that. Rotation matrix. Let's see what comes up. Rotation matrix. These guys here. Sines and cosines usually. 90 degrees. It's that guy. Yes, 1 minus 1. Beautiful. What has Wikipedia to say about it? So the rotation matrix, I'm thinking about a two-dimensional space here, is usually this thing where you put in the angle, and for 90 degrees, these guys die, and you have 1 and minus 1. That was the matrix I was using. Yeah? So literally that picture, just for this very specific angle, the 190-degree angle. And how do you turn that into a arbitrary rotation? Well, you can take the e to the e to the ta, and then you literally get a rotation by angle t. So this exponential function somehow gives you a symmetry, right? So it gives you a nice symmetry in this case, a rotation. Or if you use the matrix scalar times identity, then this is like an expansion or contraction. Or you can shear, right? If you take a nilpotent matrix, let's say a squared is 0, then this gives you a kind of a linear shear, a linear drift. So this is what this usually thing does, and it usually gives you a matrix. Yeah? So rotation matrix, expansion, a contraction matrix, and a shear matrix, or a scaling matrix maybe, and a shearing matrix. So all of these things are kind of nice matrices. And this is what the exponential map does, and this is where this slightly convoluted but absolutely beautiful picture comes into the game, which I'm zooming in a second. So essentially, let's say we have this thing. How do we actually build a curve? We could do that. Huh? We can just do that. And now we're going to have a curve in G, and this is essentially what we did, right? So if you have something in the tangent space, how do you can build a curve? Well, you do that. We'll see that here in this picture in a second. And essentially what we'll see is that the Lie algebra correspond to one parameter subgroups. And of course you only want to see how those Lie algebras usually look like, and maybe you'll find some extra structure on it. But let's zoom into this beautiful picture which I stole from here. A very absolutely amazing picture. So Lie algebra tangent space is the identity. So here Lie group is just this blob thing, which looks a bit nicer than my blob, which looks actually much nicer than my blob. Oh my goodness, it's so much better than my blob. Anyway, so this is like a transportation. Forget that. So ignore this thing at the bottom here for now. And we have this little thing here, the identity. And the tangent space at the identity will be our Lie algebra. And whenever I have something in the tangent space at the identity, like a tangent vector, for example, you can take its exponential, and it will be the curve that walks along along inside of the group, kind of following the velocity at this point, and then kind of universally, in a certain sense, universally extended to the whole group. And this whole idea is then the exponential map will get you from the tangent to the group, and there's our logarithm again. You somehow can't avoid it. It's very scary. And the logarithm somehow gets you from the group to the tangent space, so to the Lie algebra. The logarithm will be less well behaved than the exponential, so most of the time people talk about the exponential instead of the logarithm, but essentially that's the picture. So I try to say it again. An element in the tangent space is maybe this vector here, and you want to follow it and want to create something in your curvy space here, in my little blob curvy space. And the way to do this is, well, there are plenty of ways, but the kind of the universal way in a certain sense to do this is to just exponentiate it using the exponential map, and it gives you like this nice little picture. And then in the end you can even identify the Lie algebra, which in this talk, let me scroll back. In this talk, do I have it actually somewhere? In this talk, by definition, is just a tangent space as the identity, and then you can describe it nicer as literally just or nicer, in some sense nicer, as one parameter subgroups of your Lie algebra. I don't want to do that. Next time, Lie algebra and Lie matrix groups, and I forgot to take that out. That was actually something for myself. Usually I just have thank you for your attention. I will leave it here. So next time we will have those guys. Anyway, I hope you enjoyed this video, and I also hope to see you next time.